Okay. All right. So why don't we get started? People are still coming, but why don't we catch up on what we did last time, and then we can talk a little bit about the homework. We can talk a little bit about the homework for next week, and see where that puts us. So, what did we talk about last time? The most important thing of all. No, it's not the most important thing of all, but it's something that a lot of people think is very important. Quasi-geostrophic potential vorticity, right? So it's like a song even you could sing about GFD. When I was in graduate school, it really was that QGPV was like 90% of what people talked about in GFD. That was the whole thing. And so now I think it's the submesoscale, interest in the submesoscale has actually broken out of that because you can't always use QG for the submesoscale. And so I think people are thinking bigger about what GFD is about. But at the time, everyone was very excited to use QG to study mesoscale eddies and synoptic phenomena in the atmosphere, and that was everything. And people weren't so worried about the water cycle in the atmosphere, which is a big part of the difference, which you could do in QG, I guess, but they're not very effectively. And then in the ocean, when you switch to the submesoscale, like the scales get too small. You're smaller than the deformation radius for the whole depth. And so it's not and also the Rossby number starts to get big. And so the small Rossby number approximation is not very good. So as we start to learn about these pieces so that we can think about what the turbulent boundary layer looks like at different scales, we're kind of paying attention to which of these theories applies where. So what's the big story for quasi-geostrophy? How is it different from planetary geostrophy?
Horizontal scale is around deformation radius.
Yeah, so they're both small Rossby, but in the planetary geostrophy, you're so big that the deformation radius is negligibly small, which means that you keep all the terms in the thickness equation. So there's still a DDT in the leading order, and the DDT at the leading order is only in the thickness equation, or equivalently in the large-scale potential vorticity equation. But when you get to QG, it's a divergent or a non-divergent horizontally?
Geostrophic part is non-divergent.
Right. And so but the problem with that is then our governing equations, the geostrophy and the continuity equation, you lose all the DDTs. So there's no way to solve that system on its own. So we go to the next order to recover a little bit of divergence, a little bit of planetary changes in the F, and a little bit of finite Rossby number stuff. So all of those three components come in together at the correction to geostrophy plus horizontally non-divergent. And when that happens, then we get a governing equation which allows us to solve for things. And that governing equation is the quasi-geostrophic potential vorticity equation. So that's the one that's got the DDT in it. That's the one that goes. So here's the system then. So this is the governing equation, but oddly, this isn't the leading order. This is the correction to the leading order dynamics. The leading order dynamics in QG are just there is a stream function. It gives you the geostrophic velocities, and we know there's a stream function because it's incompressible. So the geostrophic stream function is incompressible, and the flow is dominantly geostrophic, is the leading order. Yeah.
So you just said that maybe we can do the atmospheric water cycle using QG.
Oh yeah.
But I think the deformation radius in the atmosphere is 1,000 kilometers.
Right.
That's much larger than the spatial scale of some ray system.
Absolutely. And so you have a big problem with whether beta y remains smaller than F naught in the atmosphere. So QG is pretty good if you're just thinking about the span of the westerlies. So you can't really do the Hadley cell, but you might be able to do the mid-latitude part of the water cycle, the eddying part. So it's not, QG can't explain the whole planet, because it has a limit on how much deviation the Coriolis parameter can have away from its central value that gets assumed when you think about the geostrophic part. But it is really useful for kind of synoptic scale atmospheric events, mesoscale ocean events, and even you can push it up to the scale a little bit bigger than that, like the gyre scale or maybe the Ferrel cell scale in the atmosphere, but not much bigger than that. Does that make sense? And weirdly, so we talked about distinguished limits. So what is a distinguished limit?
Meaning QG.
Well, QG is an example of a distinguished limit. But what is the concept of a distinguished limit? We write down these parameters, these dimensionless parameters, and then we said you take a distinguished limit, which is a limit when
some number crosses a constant, like 1 or 10.
So that's the asymptotic limit. So a distinguished limit is one example of an asymptotic limit, but a distinguished limit is when you put together multiple different dimensionless parameters in a particular way so that the equations of motion you end up with, the approximate ones, are still a reasonable system. So QG is an example, planetary geostrophy is an example, shallow water equations are an example. They're all limits of saying take this approximation and this approximation and this approximation, and QG is a really good example because we say Rossby is the same size as beta y over f naught is the same size as the deviation in thickness versus the mean thickness. So we've got 3 different dimensionless parameters, and we say they're all about the same size. So the dimensionless limit is that. Whereas, remember the distinguished limit for planetary geostrophy was Rossby is small, but Rossby times L over LD squared is order 1. So this is a distinguished limit. It's 2 different dimensionless parameters cooperating together to allow certain terms in the equations to be preserved. Because if we didn't do this, I mean, we could have easily said, we could do that and we could do this. Now we're really, really big compared to the deformation radius. But if we did this, we wouldn't have ended up with a sensible thickness equation. And if we did this, there wasn't a sensible thickness equation either unless we went to higher order, right? So distinguished limits are taking multiple dimensionless parameters, like we do for an asymptotic limit, but thinking about them collectively so that we end up at a system that makes sense. And so you could say, well, why can't I use QG if beta y, what if beta y over is bigger than f naught? Why can't I use QG then? Well, you can't because it doesn't work. The system you get, if this deviation is large compared to that, trying to write QG in the spherical, in spherical coordinates and write QG on the whole planet actually doesn't work because QG breaks down as you approach the equator. Why? F becomes small, and QG assumes that the geostrophic velocity is the dominant velocity. So you actually can't shoehorn it into working. Planetary geostrophy, very weirdly, works almost all the way to the equator, as long as the velocity stays small. So the Rossby number is actually pretty small, even down to within about 5 degrees of the equator, and planetary geostrophy works nicely from the pole all the way to 5 degrees. You can't really use it to go across the equator, but you can actually patch it on to a shallow water equation, like kind of matching condition, and then it works okay. So planetary geostrophy does not have the same problems that quasi-geostrophy does, which assumes these two go together. So the point here is that the reason why we only learn a few distinguished limits, we only learn the shallow water equations, not other limits of the Boussinesq system, the QG, PG, because those are distinguished limits that are sensible and we can think about using them. What do we do if we want to break it? What happens if I wanted to if I wanted to deviate away from a distinguished limit? What can I always do? We simplify the Boussinesq equations or simplify the Navier-Stokes equations to get to these things under certain assumptions. So what if I want to violate those assumptions? What can I always do?
You just use the full.
I can go back. It gets more expensive. It's not, like we might have to take those really fine time steps to keep the gravity waves in, or really, really fine time steps to keep the sound waves in, but it's always there. So these are approximations that make our life simpler, and we learn a lot from them, but really, when you discover something in the QG system, you probably should go back and check it in the Boussinesq system or in the Navier-Stokes equations to make sure that phenomenon doesn't somehow get messed up through the approximations that you made. Does that make sense to everybody? So these are systems that allow us to make progress on what we think the full behavior would be, but we're not sure until we go back and check. Yeah?
So is it always possible to go back and check something like that analytically without just making the same?
No, it's usually not possible analytically.
Right. So
It may require numerical solutions or observations, whatever.
So you're hoping that whatever thing you found with the distinguished limit is like robust enough to show up in some kind of numerical calculus.
Right, or the real world, yeah. And so, but the reason why QG and PG were invented and shallow water equations were invented was when computers were slow, we couldn't even do numerical, and so people wanted to do analytic work, or in the early days of numerics, they had to make a lot of approximations to do anything. Now we might say, I want to do paleoclimate, so I want to run 100,000 years of ocean circulation. I can't afford to do that in the full system or even the shallow water equations, but I could if I was using PG. So if you make what they're called Earth system models of intermediate complexity, or EMICs, they frequently have something like a quasi-geostrophic or a planetary geostrophic ocean that allows there to be some circulation, like they're gyres, and they respond to changes in the wind stress, but they're greatly simplified. So you can, in the PG system, you can take time steps of a month, and it doesn't really change the solution. So that's enormously important if you want to run, 1.2 million months in your simulation, right? Does that make sense to everybody? So that's the framing of all this. Okay, so, but the last little piece before we switch over to talking about homework that I wanted to cover was the continuously stratified. Vallis doesn't do this in detail. We're not going to do this in detail. It's the same game that we played where you say small Rossby number and et cetera, So we take the dimensionless Boussinesq equations. So now this is not the dimensionless shallow water equations, but dimensionless Boussinesq. So we get a Rossby on the DDT term. We get a hydrostatic. The mass continuity now has a vertical velocity derivative in it. And instead of a thickness equation, we have a buoyancy equation, which is, the thermodynamic piece. So when we went to the shallow water equations, we assume that densities aren't changing. You're not jumping out of one layer into the next layer below like that. So whether we were in the full depth system, which was the water is just the water, or in the reduced gravity system, the difference between our different layers was what their density was. So in the Boussinesq system, you could be transforming your buoyancy, you could be getting mixed, or you could be, getting heated or cooled. That's why the 3D system is more interesting than the 2D system. So instead of the thickness equation, we have this equation, which brings us a new variable. So now we have to look at the thermodynamics. And so here's the new variable appearing in the thermodynamics as well. But again, we just see the same old parameters that we're used to, L over LD squared, Rossby. So it's not surprising that there is a PG system and a QG system underlying this. And we can still see, good. So if we take small Rossby, L over LD much greater than 1, such that Rossby L over LD squared is order 1. What system am I looking for here? Planetary. Same assumptions. Take those dimensionless equations, rewrite them. We see that buoyancy is conserved. Hydrostatic balance. 3D incompressible. Not 2D. 3D. And and geostrophy. So where's our DDT? The buoyancy. So remember in the planetary, shallow water planetary, we had thickness equation was giving us an ability to evolve. So now in this system, it's the buoyancy that's giving us an ability to evolve. Just like last time, we could also write this as potential vorticity and have that be governing instead of this. If we do that, then this becomes our potential vorticity. I'm gonna write this one down because this is a funny thing. So the potential vorticity, and that is this instead of, I don't even know what I'm gonna write, shallow water. This is F over H. Okay, so how do I understand, how does that work? Why is that the same concept? So why do we have F upstairs and H downstairs? Well, so potential vorticity, right? It's the idea that if you stretch in the vertical, then you spin up your vorticity, and if you squash in the vertical, you slow down your vorticity. So you take the ratio of those things, and that's constant, right? So that's this one. How is that the same as this?
We can understand it as many layers as signal.
Right, so imagine little layers, each with a slightly increasing buoyancy. dBdz tells you how stacked they are. If you squish them, dBdz goes up. If you stretch them, dBdz goes down. And so when F, if you squish them, F goes, or F plus zeta would go down, but dBdz would go up, and inversely. So that's the same idea. These don't have the same units anymore because, as we said last time, QG doesn't really have units. It's a concept more than a particular metric, which is super frustrating because they could very easily have the same units if they chose to write it that way. But anyway, this is the standard. Sometimes people call this one the Ertel potential vorticity, or really, we're going to talk more about this, Ertel, which is F plus omega, so the 3D vorticity, dotted into the gradient of a conserved thing like buoyancy. So we're going to see that this one is actually conserved by the full Boussinesq system. So this one is kind of the continuous PV. But here, for our simple case, this one is just F dBdz, and since we can take all the derivatives and figure out, what system we'd need, but this is equivalent to that one. So you can have either one. What about QG? What are our limits going to be? L and LD about the same size. Rossby small. Planetary, so beta y over f naught being small, same size as Rossby, and curly h deviations in thickness compared to thickness, average thickness, small order Rossby. All those are going to go together. So the Rossby number is small, flow is near geostrophic, the scales of motions are similar to deformation scales, the variations of the core parameter are small, and there's also the curvy h one, which you can derive from these three. So we take those same Boussinesq primitive dimensionless equations. We play the same game. So here's the Boussinesq system. Same Boussinesq system we just looked at. There were no approximations beyond Boussinesq by just writing how big these terms are. We haven't thrown anything away. So this is still the full Boussinesq system. But now we start throwing things away. We form a vorticity equation. We form a buoyancy equation, which again has the W in it. And then here's maybe the way to think of how we get to the PV system is we're trying to kill the W between these two equations. If we eliminate W, then we end up with something that looks like this. Look at this. How does this version of the Q compare to the version from the shallow water QG? shallow water QG was Q equals del squared psi plus beta, or plus F plus, what else have we got? Yeah, eta over H F naught. So how does this one compare? So what's zeta G? Zeta G is our vorticity, which is dV, dx minus du, dy. It's the geostrophic vorticity to leading order, which is the same thing as the stream function square, or Laplacian the stream function. So this part is the same. This is the same between the systems. Except in this one, it was like the geostrophic velocity of the whole layer. Here it's now at every depth. There is a stream function, and we take the horizontal Laplacian of that stream function, and that's what it goes to. F is the same in both, and it's F not F naught, has the beta piece in it. What's this crazy thing? D by dz F naught beta prime over n squared. You can think about it like this. If I'm lifting up the layers, I would have a thickness anomaly, eta, but I would also have a buoyancy anomaly. Because I was maybe excessively dense or excessively light as I was moving the layers up and down. This buoyancy, ddz of that, is the same in the same way that this was telling you about the stretching and squeezing, the same way that H was here. This ddz of buoyancy over n squared is giving you a local stretching. So it's playing the same role as eta over H here. Eta over H is a stretching. ddz of buoyancy over n squared is also a stretching. That makes sense to everybody? Okay, let me see if I wrote it the other way. So this one's a little more complicated because now if I look at this, like, how do I find out the geostrophic velocity from this? And also, I've got a ddz here now. What's the boundary condition? If I've got to integrate this in the vertical, I've got a new boundary condition at the surface that's ddz of something. Because I don't just have horizontal boundary conditions like I did before. So it's important, this comes, in the continuous system, this comes along with a lot of extra pieces. So the horizontal velocity is a vertical curl of that stream function. That looks really similar, except it's now continuous. In 3D, we have this operation. The relative vorticity, zeta, is Laplacian, just like we wrote there. The perturbation buoyancy, this is a magic connection. Beta prime is F naught d psi dz. So the buoyancy perturbation is linked to the stream function perturbation. Why is that? Not quite. Buoyancy could also change because of horizontal motion. We have, but you could have like a warm anomaly here and just slide it sideways, and then it would be it could be evolving that way. What's our balance? Just like the geostrophic balance that we have when we have hydrostatic and geostrophic together. What was that? The thermal wind. And the thermal wind relates horizontal deviations in buoyancy to shear in the velocity, horizontal gradients in the buoyancy, Or if you want to think of stream function as pressure, it's pressure over F. The pressure, this is also the hydrostatic balance. D pressure dz, with some funny F naught because of units, is coming from the buoyancy. So this is the hydrostatic relation rewritten in this buoyancy stream function formulation. And this also tells us how we should set vertical boundary conditions. We need to know something about the buoyancy at the surface to set a vertical boundary condition on the stream function. Okay? So we're going to make a little bit more hay out of this in a little bit, but here is two ways of writing different vertical boundary conditions you might want. You might have W equals 0, can't go through the ground at the bottom, and this is the way you write it in stream function form. Or you might think of the buoyancy being a conserved thing that's sliding around on the surface, and then the buoyancy changes this, which gives you a boundary condition on the stream function, which allows you to solve the original equation. Okay, the last piece of information I want to show. I don't know if I could move myself out of the way. So once we've written that little, once we've written that little buoyancy equation piece, let me go back. This is the way of understanding that the buoyancy perturbation has to do with stretching. But once I have that relationship on the next page and I say, oh, hydrostatic tells me that my buoyancy perturbation is related to stream function, I can plug it back in, and then I get this. All right, here's the master challenge. If this is a horizontal Laplacian, and this has two dd's in it, what does it look like? If n squared was constant,
Diffusion kind of.
it looks like, the horizontal Laplacian plus ddz squared, that's the 3D Laplacian. But it's not quite the 3D Laplacian because there's this funny f squared over n squared term in it. So what does the f squared over n squared term do? Let me write that down for here. F squared over n squared, something that we might think of as a vertical scale of motion, ddz squared. What is that starting to look like to you?
The vertical axis is stretched to NH over F.
The vertical axis is stretched to nh over f, or it looks like L over LD. So what this is it's a 3D Laplacian of the stream function, but in a coordinate system that's rescaled so that the vertical scale is measured in units that are most meaningful for the deformation radius. So the deformation radius is coming back into play. We know that the deformation radius is really important here. It's saying which vertical scale is the scale that the changes are important on, which we know is related to hydrostatic and geostrophic balances. We've been talking about that all along. Here it is coming back and saying, this looks an awful lot like PV equals the 3D vorticity plus the planetary part. That's what it looks like, except we have to stretch the vertical coordinate system first, because deviations in the vertical are happening on smaller scales than deviations in the horizontal because of this. Does that make sense to everybody? So I know this is a lot of magic at the moment. We're going to see these equations. We're going to come back to them as we think about things as we go on. Oh, I'm going to leave the Ekman part. This is too complicated for us to do justice to. I have one slide on it, but we'll talk about it on Monday. We'll leave that part aside for now. All right. So should we talk a little bit about the homework before we run out of time? Do people have issues, questions? What happened in your assessment of what? Oh, how do I do this? want that one to be on top. Which one is this? That's the wrong one. So homework for next week is basically just on QG and PG. And it's a lot of just estimating things. So carry through the derivation of the quasi-geostrophic system with the anelastic system instead of the Boussinesque. So it's like revisit the derivation, but do it in a slightly different form. Shallow water planetary geostrophic equations can be derived by omitting this. So this is going back to small Rossby number approximation. You're going to show how that works in more detail. We've said it casually in class and kind of waved our hands at it. You'll dig into a little more into that. This is thinking through how wind stress appears in the equations for an Ekman layer. And then this piece, which we're going to talk about Ekman layers on Monday. And then this is another bigger Ekman layer conversation we're going to have for Monday. So I'm going to leave those till Monday. Necessary conditions for instability. Oh, this is, sorry, we do have one problem that's going to come from instability stuff. So we'll start talking about instability enough to get this piece. Next week is all about chapter 8. Okay? So not too many questions, but I think this Ekman, like I was saying before, I think this Ekman layer problem is pretty involved. So fewer questions, but this one is one that's going to take a while, I think. The first two should be pretty straightforward, just following the derivations in the book with different, slightly different assumptions. Okay, let's talk about the homework from this time. So what did people find, or were there any problems that were particularly confusing? Yes, no.
Yeah.
Yeah. All right, which one?
Um,
All of them. Yeah.
Plenty of them. I remember being confused by the one where you had to, like the first one where you had to plug in actual numbers of like the atmosphere
This one?
data. Yeah. The
Yeah.
second bit of that, I wasn't sure how to go about getting the potential density.
Yes. It is extremely hard to do it. Valis really hasn't given you enough information. The way that I found the potential density, which was what I was hoping you guys might find, was I just went and found a figure that had potential density in it. That was how I got it. Somebody else had produced a figure, Lynn Talley, who teaches a class similar to my intro to oceanography class at Scripps. She has a bunch of stuff online. This is a nice figure. That's the simple way to do it. The real way to do it is significantly more complicated in the ocean than it is in the atmosphere. Why?
The equation's different.
Yeah, we don't have the ideal gas law.
Yeah.
And so the ocean equation, seawater equation of state is like super complicated. It's got like salinity and temperature and this weird compressibility effect. And so Valis doesn't even write down an interesting approximation to it. The UN standard is a 72-term polynomial. So we don't tend to actually calculate the seawater equation of state very accurately. There's like a MATLAB toolbox that helps you do it. But really, a simple way to think about it, and why this problem is a really good one, is just find somebody else who knew what they were doing, who calculated it. Yeah, but I agree. It's super complicated. And then this last part, in the abyss, so I just pulled it off that same figure, but I'll tell you there's a secret in the way you calculate the potential density. You have to have a reference pressure. And so this one is calculated with a reference pressure at the surface, which means that the potential densities are actually pretty accurate up here. But look at this. Do you see how the potential density is denser above something that's less dense? Why doesn't that happen? Can that happen? Does that make sense? This figure is telling me that water is denser than this water. And so what would happen if that was the case? If you put cold stuff on top of warm stuff, what happens? It convects. This is stable for the 130 years of deep ocean observations. We keep finding this above that?
Can we estimate the time scale it needs to condense?
You can, and it would be hours.
Okay.
That's not the right answer. And it's because the nonlinear equation of state has a coupling between ambient pressure and the amount of potential density variation that goes with salinity and temperature, which is something we have not talked about at all in this class, and it's a total nightmare. But this reference pressure at the surface means that this approximation is only accurate up here. We should actually take a reference pressure at 4,000 meters, and then it becomes stably stratified. So this is a total nightmare, and it's not a surprise that it was difficult to find it. I think what Jeff's trying to Jeff Vallis is trying to motivate people to do with these, like go hunt on the internet for numbers, is to think about how could I find something that is close enough to what I want from a trusted source. I think he's encouraging you to use the internet to figure that out. So that's why I like these problems, but at the same time, they're kind of not fair, and we're definitely not going to get the same answer. And in this case, even though this is from a trusted source, a good web page, it isn't the appropriate definition of potential density. So if you calculate it from this too carefully, you would have found a negative stratification. Your buoyancy frequency would have been imaginary. So it's not imaginary. Actually, things are weakly stratified in the abyss. It's just, and so I solved this by just looking over here where it was stably stratified. So I just picked a number down there, but this actually is probably a pretty poor estimate, because we really should have been much more careful to use a potential density that was appropriate for the ocean abyss to get it right. This is something we talk about much more in the oceanography class than in this class, but Jeff's really pushing hard. And the stratosphere also, did anybody have trouble figuring this one out? Because this one's really confusing, because the stratosphere, it's less stratified than the troposphere. But we always say the stratosphere is the stratified one. What does that mean? Anybody figure out what this is about?
It's just shorter.
Yes, it's because of the Z. This is a DDZ. The stratosphere is stratified in pressure coordinates, but because the pressure is expanding exponentially, the differences in pressure is expanding exponentially, it's taller, even though per unit pressure, the density goes up more. Per unit distance, it's not as much.
So I think you get this result just because you use the wrong data. I think the stratosphere is more stratified if we
Even in Z coordinates, you think?
Yeah.
It's it is entirely possible that this estimate is a poor one, because I was just pulling it off of these two figures. And so I was basically taking this amount over, those pressure levels, and then pulling this depth off of this one, which is, 40 kilometers tall, to go that many units of pressure, which is still ballpark right, but this might have been more compressed.
Yeah, because the temperature gradient is too large in the stratosphere, so it cannot be plotted on this figure.
Yeah. So could also be that these up here are too messy. Okay, but so so Ming-Chi sent me a much better version of the data for the stratosphere potential temperatures, and it is much cleaner in the version that he found. But again, like estimating from this is probably was pushing it too far. So, but anyway, it is still whatever. This is the piece that's nice about this is that it allows you to think like, do I mean vertical distance in pressure, vertical distance in Z? What's the definition for the buoyancy frequency? What does that really mean to me? A lot of things. Does that make sense to everybody? Yeah.
This is kind of late in the semester for this question, but what exactly does stratified mean?
Good. No, stratified means that the dense stuff is at the bottom and the light stuff is at the top.
Okay.
That's what we really mean. But then we use it colloquially. This is a super irritating feature of atmosphere and ocean scientists. We then abuse that term and say that the temperature is stratified, or the nutrients are stratified, or the whatever, because once we've got that concept in our head that there's like different value at the bottom and from the top, then we start talking about stratification for anything that has a vertical gradient. But really what we mean by stratification in the cleanest, simplest form is we mean that there is a potential temperature or potential density increase in the vertical in such a way that a displacement of a parcel would bring it back to where it started. Because if you push up something dense, it comes back to where it started. If you push down something buoyant, it comes back to where it started. So the buoyancy frequency being not imaginary, that thing being a restorative piece is what we mean by stratified, at least locally.
Is there a word for when it isn't restorative?
Yeah, so you might say stably stratified, which would mean that it is stable in that vertical gradient, or unstably stratified is when it would overturn on its own, when it's primed for convection. Or neutrally stratified is when there's no vertical derivative in potential temperature. So the troposphere is close to neutrally stratified because it's getting mixed by storms and things, not convectively, but reducing gradients in potential temperature, not in situ temperature. Yeah, yeah. In the tropics. Sorry, not everywhere, but yes.
I mean, do we also always need to assume a local Fox-Kemper to have the definition of stratification?
No, you can write, there's an equivalent of stratification in the anelastic equations in the atmosphere, so it doesn't have to be Boussinesq. So you can do it from anelastic pretty simply. You can do it in the ocean. It gets really tricky if you want to go big distances and say, is it stably stratified over long ranges? And in the atmosphere, it's very tricky to say whether you're stable, including the moisture. Because in the atmosphere, when something ascends, it expands, it cools, and the rain falls out. And then its density is changed by the loss of the moisture, descending air and ascending air have really different relationships of the density as a function of pressure. So it's not, the real full system is more complicated, but Boussinesq makes it easy, and anelastic is also pretty easy. And so pressure coordinates in the atmosphere make it pretty easy, but still complicated. So all right, so was there another one that's worth discussing for a few minutes? Well, we have 5 minutes or so. Yeah, and my answer key is much simpler than the discussion we just had, and that's the intention of the level of understanding that I'm expecting you to get here, is like to just recognize that some of these problems are super complicated. There's a lot more here, but like, can you just extract the one piece that's a ballpark of the question that it has? And so that, I think what Valis is really after is for you to figure out how to use the internet to your advantage to find things like this quickly. And plus some distinction about like the time scales in the troposphere, stratosphere, picnic line, and abyss.
Can we talk about the next one?
Yeah. Oh yeah, so like 4 of them are all related to each other. So if you got this one cleanly, then the remaining 4 would have all been pretty straightforward to get back from this one. So what's the trick here? This is the major trick, this little piece. So this is just a Fourier transform of the surface height. But if the different Fourier modes don't interact, you can solve for them one at a time. And that makes it really much simpler because every Fourier mode has a length scale, so you know what L over LD is for all of them, and so you can play that game over and over again. Does that make sense to everybody? So first we got to linearize. Did anybody have trouble linearizing, or is that clear how to do that now? basically you think which of these terms are big and which are small. And so eta is small, but big H is big. So you don't have eta times u because we're perturbing about a state of rest. So u is small, and so eta times u is small, but h times u is not small. And so you're just keeping the first perturbation, the first thing that you might want to keep out of this. That's the linearization. You don't have any quadratic terms, so it makes it a linear system, which you can then solve. So here are the initial conditions, and Ming-Chi pointed out that in one of the later problems I did not simplify this sufficiently, that the initial conditions in one of them also had a velocity initial condition, which I did not solve. I argued it from intuition, but you could have done that much more specifically. So first you have to calculate the PV from that surface height. So we're following like the geostrophic adjustment thought process. And then that becomes this. And then I introduce this new notation because I don't like writing EDIK plus ILY. So when I removed the tilde, I implied that it was absorbed inside, which notation is very helpful. Anyway, so then you can write out the vorticity from that. You can write out the Laplacian. You can solve the Laplacian. So here, normally to get from the surface height to the vorticity is complicated. You actually have to use a numerical solution. But once you're in Fourier modes, you just divide by k squared plus L squared. So you can invert all of the equations in the Fourier basis very simply. Does everybody see how to do that? Ish. Okay. And then we talk about the waves propagating away, which doesn't really make sense. You could also have kept all the waves banging around in here, but I don't think Vallis wanted you to. You could either argue that the waves were damped out or that somehow the Fourier basis didn't go all the way to infinity, even though it does. Whatever. This is a casualness that whatever. If you do that, then you can play the same game that we do for geostrophic adjustment, which just says that the PV, we need something that is both in geostrophic balance. So that means that there's this relationship between eta and zeta. And that's the PV is the same as it was in the initial conditions. Why is it the same as it was in the initial conditions? Because it's conserved, and in the linearized system, it just becomes a partial derivative with respect to time of Q, which means that Q doesn't change in time. So once we have the initial Q field, that's the Q field for all time. Okay? And so if you make that assumption, then this is your governing equation, and look, it's got an eta and an eta, and so you just solve for eta, wherever it is, that's what it is. So it gets this funny 1 plus LD squared k squared plus L squared. So what is that thing? Yeah, LD over L squared. It's the same thing, it's this, that we keep writing everywhere. It's just that written in Fourier basis. So great. So that's the reduction factor. So if you're much larger scale, that is k squared plus L squared, is small, then you get the same surface height as the initial one at the final time. If, on the other hand, k squared plus L squared is really big, then your final condition is eta equals 0. So that's the tipping point. The things that are bigger than the deformation radius are preserved because they come into geostrophic balance. The things that are smaller don't. They dissipate. Or actually, they turn into gravity waves if we were tracking the gravity waves and not forgetting about them. Does that make sense to everybody? And then you go through the process of calculating the energy is basically just figuring out the definition of the energy that makes sense, plugging in, and then you get that. And the interesting point about the energy is that the final energy has a ratio of that thing over that thing, which tells you that the total energy is conserved at very large scales because basically all of the initial energy ends up geostrophically balanced and stays put, whereas if it's the wave-like energy, it would have propagated away, and so it would have been lost. Does that make sense to everybody? what if I had kept the waves in? What would have happened when I got to this energy? The energy wouldn't have changed, and it would have been a bigger struggle because I would have had a stationary part of the energy that would have looked just like this, but then I would have had a time evolving part of the energy that would have been exchanging back and forth at every point in space between gravity waves potential and gravity wave kinetic. They would have been equal to each other, kinetic plus potential, and they would have been propagating around, and so you would have had to calculate both the kinetic and potential part and figure out what that was all about. It would have been related to the time-dependent part of this solution. But in the geostrophic adjustment piece, we've lost those, and so the energy can decrease because those are just removed. Does that make sense to everybody? And then the other ones, quickly before we go, so it's approximately geostrophically balanced, so that's true. There's the energy, and you can break it down into the kinetic energy part and the potential energy part. And the really interesting thing in this case is that if you're where L equals LG, the kinetic and potential energy are equal. If you are on scales smaller than LG, the kinetic energy is bigger than the potential energy. If you are on scales larger than LD, the potential energy is bigger than the kinetic energy. So that's actually really useful. And when we look in the atmosphere and we look in the ocean, on large scales, the potential energy is much greater than the kinetic energy. And on small scales, the kinetic energy is much greater than the potential energy. And the tipping point is the deformation radius. So that's a really useful thing to keep in mind as we talk about the exchanges between kinetic and potential energy as we go on. All right. I'm not going to talk about that one, but you can take a look at those. Oh, and sorry, I didn't realize when I was looking at these, this one is fine, but this one says using that equation, which I'm sure nobody had that equation. So sorry, my apologies. I was hoping you were going to figure it out anyway, but if you don't, whatever, no problem. Okay, thanks everybody. So next week we will start talking about instabilities, and we'll do the Ekman layer first, which should just be 10 minutes or so on Monday, and then we'll do the instabilities for the rest of the time. And then the following week we do turbulence, but we're just going to I'm going to be away on Wednesday and Friday before spring break, so you get an extra long break. But so we'll start talking about turbulence, then there'll be a long break, and then we'll come back. So there'll be a homework that's mostly instabilities for the one that comes the following one. A little bit of turbulence, maybe. Does that make sense, everybody? All right.